Today we discuss about the structural elucidation of alkaloids. Structural elucidation means structural determination of unknown organic compound or unknown alkaloid. There are number of techniques that can help us to determine the molecular structure of unknown alkaloid. In this process, first of all, we determine the empirical formula and also determine the molecular formula of the unknown alkaloid. After that, we determine which kind of functional group is present in unknown alkaloid and also determine the nature of nitrogen present in unknown alkaloid. As the molecular structure of alkaloid is quite complex, very little progress was achieved in the elucidation of their structures during 19th century. But now the new methods for the determination of unknown substances are known. The following pattern of procedure is adopted to establish the molecular structure of an alkaloid. Now let us go to the molecular formula determination. After a pure specimen has been obtained, its elemental composition and hence the empirical formula is found by combustion analysis. Then its molecular weight is determined by the RAST process to establish its molecular formula. Its calculation is based upon the simple fact that introduction of a double bond or cyclization of the chain decreases the molecular formula by two hydrogen atoms relative to the corresponding saturated aliphatic hydrocarbon. Next, functional group analysis. Application of classical techniques of organic analysis and or infrared examination can reveal the nature of the functional group present. If the alkaloid is available in appreciable amounts, classical techniques of organic analysis are used. If the alkaloid is available only in small amounts, infrared examination is used. This will also reveal the aromatic or aliphatic nature of the alkaloid and the unsaturation if the present. Unsaturation is determined we use two simple laboratory reagents like bromine water and KMnO4. Functional nature of oxygen. If an alkaloid contains oxygen, it may be present as OH, OCH3, OCOCH3, OCOC6H5, COOH, COOK, or C double bond O. If an alkaloid contains oxygen, it may be present as phenolic or alcoholic, methoxy or acetoxy or benzoyl or carboxylic or carboxylate or carbonyl. Occasionally, lactone ring systems have also been encountered. These functions have been detected by the usual methods of organic analysis, including infrared examination. Various oxygen functional groups can be characterized according to the following characteristics. Next one, hydroxyl group. Its presence in an alkaloid. Hydroxyl group is present in an alkaloid can be ascertained by the formation of acetate on treatment with acetic anhydride or acetyl chloride, or by the formation of benzoate on treatment with benzyl chloride in the presence of sodium hydroxide. Hydroxyl group is treated with acetic anhydride or acetyl chloride. Acetates are formed. Hydroxyl group is treated with acetic anhydride or acetyl chloride. Acetates are formed. If the hydroxyl group is treated with benzoyl chloride, benzoate is formed. However, the above tests for oxygen should be applied carefully because primary amines, if present in an alkaloid, also yield acetyl and benzyl derivatives. Then the number of hydroxyl group is determined by acetylation or Zervintov's method. In the former method, the number of hydroxyl groups is determined by acetylating the alkaloid and hydrolyzing the acetyl derivative with an unknown with an known volume of 1 normal NaOH. Hydroxyl group is treated with acetyl chloride. Acetate is formed. This acetate is treated with sodium hydroxide. Alcohol and sodium acetate are formed. The excess of alkali is estimated by titration with a standard solution of HCl. The number of acetyl groups or hydroxyl groups can be calculated from the volume of alkali used for hydrolysis. Carboxylic group. Another group is carboxyl group. The solubility of an alkaloid in aqueous sodium carbonate or ammonia reveals the presence of carboxylic group. The formation of ester on treatment with an alcohol also reveals the presence of carboxyl group. The number of carboxylic groups may be determined by volumetrically by titration against a standard barium hydroxide solution using phenolphthalein as an indicator or gravimetrically by silver salt method. Next one is oxo group. Oxo group is known as carbonyl group. The presence of this group is ascertained by the reaction of an alkaloid with hydroxylamine, semi-carbazide or phenylhydrazine and the corresponding oxime, semi-carbazone or phenylhydrazone are formed. Oxo group is or carbonyl group is treated with hydroxylamine. Oxime is formed. Carbonyl group is treated with semi-carbazide. Semi-carbazone is formed. And another one, carbonyl group or oxo group is treated with phenylhydrazine. phenyl hydrazone is formed. Distinction between an aldehyde and a ketone can be made on the basis of reduction and oxidation reactions. Next one, methoxy group. The detection of this group and its number may be determined by the G-cell determination analogous to the Herzig-Meyer method for N-methyl groups. The detection of methoxy group or OCH3 group and its number may be determined by the G-cell determination analogous to the Herzig-Meyer method for N-methyl groups. In this method, a known weight of alkaloid is treated with hydroiodic acid at its boiling point when the methoxyl groups are thereby converted into methyl iodide, which is then absorbed by ethanolic silver nitrate, and the precipitated silver iodide is filtered, dried, and weighed. From the weight of silver iodide, the number of methoxyl groups may be calculated. So, in the unknown alkaloid, to determine the methoxy group, J-cell method is used. In this method, OCH3 group is treated with HI hydroiodic acid. Methyl group is converted into methyl iodide. This methyl iodide is treated with silver nitrate. Silver iodide precipitate is formed. From the weight of silver iodide, the number of methoxyl groups may be calculated. Next one, for example, papaverine, its molecular formula is C20H21O4N. When treated with hydrogen iodide, consumes 4 moles of hydrogen iodide, producing 4 moles of silver iodide, and thus confirming the presence of 4 OCH3 groups. Papaverine, we take papaverine, its molecular formula is C20H21O4N. It is treated with 4HI, 4 hydrogen iodide, 4 moles of hydrogen iodide. In this reaction, 4 moles of methyl iodide is formed. So, 4 moles of hydrogen iodide is consumed. So, in this alkaloid, in this unknown alkaloid, 4 moles of OCH3 groups are present. Next one is ester and amide groups. These groups can be detected and estimated by observing the products of their alkali or acid hydrolysis. For example, amide group CONH2 group is treated with NaOH. It is converted into COONA and ammonia. Nature of nitrogen. Another important one is nature of nitrogen. All alkaloids contain nitrogen. We know most of the alkaloids containing nitrogen atom. Due to this nitrogen atom, alkaloids exhibit basic nature. So, all alkaloids containing nitrogen atom, but in the majority of the alkaloids, it is present as a part of a heterocyclic system. Therefore, it must be either a secondary or tertiary. However, there are phenyl alkylamine type of alkaloids, for example, adrenaline, ephedrine, which do not contain nitrogen as a part of a heterocyclic ring, but in the form of a primary amine group. The general reactions of the alkaloid with acetic anhydride, methyl iodide, and nitrous acid often show the nature of nitrogen. If the alkaloid reacts with 1 mole of methyl iodide to form an N-methyl derivative, it means that a secondary nitrogen atom is present. N-methyl derivative is formed. It means that a secondary nitrogen atom is present in a unknown alkaloid. For example, quinine, its molecular formula is C8H17N, reacts with 1 mole of methyl iodide to form an N-methyl derivative, indicating that quinine must contain secondary nitrogen atom. We check quinine, its molecular formula is C8H17N. It is also written as C8H16NH. This is treated with methyl iodide. Methyl iodide. So N-methyl derivative is formed. This N-methyl derivative indicating that quinine must containing secondary nitrogen atom. If an alkaloid reacts additively with 1 mole of methyl iodide to form crystalline quaternary salt, this indicates that nitrogen atom present in this alkaloid is tertiary. For example, nicotine reacts additively with 2 moles of methyl iodide, indicating that it contains both nitrogen atoms as tertiary. We take nicotine. Nicotine is treated with methyl iodide. These two nitrogen atoms are converted into quaternary nitrogen atoms. So, this reaction indicates that it contains both nitrogen atoms as tertiary nitrogen atoms. One can detect the tertiary nitrogen atom in an alkaloid by treating it with 30% hydrogen peroxide when tertiary nitrogen is oxidized to amine oxide. Okay. Next one, another one is Herzig-Meyer's method. Herzig-Meyer method is used to detect by distillation of alkaloid with soda lime when methylamine is obtained. For example, nicotine on heating with soda lime yields methylamine, indicating that it must contain a N-methyl group. Okay, we take nicotine. Nicotine is treated with soda lime. Methylamine is formed. Is indicating that it must containing a N-methyl group. Nicotine must containing a N-methyl group. So Herzig-Meyer method is used to identify the N-methyl groups. Next one, degradation of alkaloids. The reactions used in degradation of alkaloids are as follows. In these, first one is offman access to methylation method. Second one, amidase degradation method, and many other methods are used. Offman access to methylation method, very important method. The principle of this method is that compounds which contain the structural unit like double bond CH, double bond C, bond N is treated with trialkyl alcohol, eliminate a trialkyl amine on pyrolysis at 200 degrees centigrade or above to yield an olefin. Okay, in this method we take CH3, CH2, CH2, N, Me2. This is treated with methyl iodide followed by treated with Az2O. In this reaction, we obtain quaternary ammonium hydroxide. Quaternary ammonium hydroxide is heated at 200 degrees centigrade. Olefin is formed and tertiary nitrogen is eliminated. If the nitrogen atom forms a part of a cyclic structure, two or three such cycles are essential to liberate the nitrogen and expose the carbon skeleton. If the nitrogen atoms forms a part of a cyclic structure, two or three such cycles are essential to liberate the nitrogen and expose the carbon skeleton. However, this method is applicable only to reduced ring systems such as piperidine and actually fails with analogous unsaturated compound such as pyridine, and therefore the latter should be first of all converted into the former. In this offman degradation method, we take pyridine. Pyridine is reduced by piperidine. Pyridine is reduced by using nickel or platinum or palladium reagents. We get piperidine. This piperidine is undergo methylation reaction. That means this piperidine is treated with methyl iodide. We get dimethyl piperidinium iodide. Dimethyl piperidinium iodide is formed. It is generally called as quaternary ammonium iodide. Is also called as quaternary ammonium iodide. This dimethyl piperidinium iodide is treated with silver hydroxide AzOH or Az2O obtained dimethyl piperidinium hydroxide. Dimethyl piperidinium hydroxide is generally called as quaternary ammonium hydroxide is formed. This quaternary ammonium hydroxide is heated, pentyl dimethyl amine is formed. Pentyl dimethyl amine is formed. This is also called as NN dimethyl pentene. This NN dimethyl pentene undergo first of all methylation reaction and further Az2O or AzOH. Quaternary ammonium hydroxide is formed. This quaternary ammonium hydroxide is heated, olefin is formed, and nitrogen is eliminated to tertiary amine. Nitrogen atom is eliminated as tertiary amine. This olefin is undergoes isomerizes converted into piperylene. Okay, in this offman degradation method, we take pyridine. Pyridine is reduced to piperidine by using nickel or platinum or palladium reagents. This piperidine is treated with methyl iodide, obtained dimethyl pyridinium iodide. Dimethyl piperidinium iodide is formed, is also called as quaternary ammonium iodide. This is treated with Az2O or AzOH. Dimethyl piperidinium hydroxide is formed. This is also called as quaternary ammonium hydroxide. This is heated pentyl dimethyl amine is formed. It is also called as NN-dimethyl pentene. This NN-dimethyl pentene undergoes methylation reaction and followed by Az2O or AzOH. Quaternary ammonium hydroxide is formed. This quaternary ammonium hydroxide is heated. Nitrogen is eliminated to tertiary amine and olefin is formed. This olefin undergoes isomerization reaction. Finally, we get piperine. When a molecule of water is eliminated from quaternary ammonium hydroxide, hydrogen atom always eliminated from the beta position. If this hydrogen is not available, the reaction fails. Some physical methods are used. In alkaloid chemistry, the most important instrumental methods are as follows. First one is ultraviolet spectroscopy. Second one is infrared spectroscopy. Third one is mass spectroscopy. Fourth one is optically rotatory dispersion and circular dichroism. Next one, conformational analysis, and final one is X-ray diffraction method. Okay. Finally, synthesis of the alkaloid is the final confirmation of the structure of the alkaloid. Okay, students, I hope you understood this topic. Okay.